lesson we're going to be looking at organic chemistry, which includes crude oil, hydrocarbons and fractional distillation. Firstly, let's consider crude oil. Now, crude oil is a finite resource, and by finite we mean it's in limited supply. So eventually the crude oil is going to run out. When we talk about it being ancient biomass, that these plants and animals died millions and millions of years ago. So that's how long it took for the crude oil to form, which is why it is a fossil fuel. Now, crude oil, when it's taken out of the ground, it is mainly a mixture of hydrocarbons. So if you pause your video now and have a go with each of these to say whether they are a hydrocarbon or they're not. Remember to look at the definition. Hydrocarbons are molecules that contain hydrogen and carbon atoms only. So now if we go through these, look at the first one. We have 2 carbon atoms joined to 6 hydrogen atoms. So that only has carbon and hydrogen. That is a hydrocarbon. If we look at the second molecule, we have hydrogens joined to oxygens. So that is not a hydrocarbon. If we look at our third molecule, we have 8 carbon atoms and 16 hydrogen atoms. So only carbon and hydrogen atoms, that would be a hydrocarbon. If we look at our next molecule, we have carbon joined to oxygen. So that would not be a hydrocarbon. And then lastly, we have 5 carbons, 11 hydrogen atoms and 1 oxygen atom at the end. So that would not be a hydrocarbon. Crude oil is a mixture of hydrocarbons. So we have hydrocarbons with small lengths and hydrocarbons with longer lengths in there. So in order for the crude oil to be useful, we have to separate them out. And the process that we use to separate them out is fractional distillation. And we can see a fractional distillation column here. So the first part to separating out the fractions is that before we can do anything, we have to heat the crude oil. And the reason why we heat the crude oil is because we need the hydrocarbons to evaporate and become vapour. The vapour will then enter the fractional distillation column, and the smaller chain length hydrocarbons will rise up higher in the fractional distillation column. And when they reach a specific point in the fractional distillation column, they will then cool and condense and turn into a liquid. The liquid can then be collected and used as a fraction. So the key thing is that we are wanting to have fractions of hydrocarbons with similar chain lengths. Now, as we can see, the lowest boiling points are at the top of the fractionating column, and as the molecules become longer and longer and longer, their boiling points increase as we go down the fractionating column. So the first trend is that the boiling points increase down the column. So I'm going to write it like this: boiling point with my arrow going downwards, which means the boiling points increase as we come down. Now the next trend is how flammable these molecules are. Now in terms of how flammable they are, the most flammable hydrocarbons are going to be towards the top of my fractionating column, because they're smaller molecules, they ignite and they will burn much more easily than the longer hydrocarbons with the higher boiling points at the bottom. The next trend is to do with viscosity. Now viscosity, just write that in first. Now viscosity is to do with how easily a fluid flows, and the harder it is for the fluid to flow, the more viscous it is. So for example, treacle is very viscous. It's very thick and it's very gloopy. It doesn't flow very easily. Whereas if you have something like water, water flows very easily, so it's not very viscous. Now, we've gone through how fractional distillation works and the trends as we go down the column or as we go up the column. What would be a good way of revising would be maybe to make yourself a flashcard with the important information on, and if you do something like that and you highlight the key terms, it will help you remember, just in case this comes up as a 4 or 5 mark question, which it can quite easily do. Now for this next part, we are going to consider 2 different types of our hydrocarbons. We are going to look at hydrocarbons which are alkanes, and we are going to look at hydrocarbons which are alkenes. Now, first of all, hydrocarbons that are alkanes, they only contain carbon to carbon single bonds. And alkenes will contain a carbon to carbon double bond. So they have a double bond in them. And due to this, we say that alkanes are saturated. So they have as many bonds as they can do. And alkenes, we say, are unsaturated, because this double bond could potentially open up and join to something else. Now, the key thing about looking at alkanes and alkenes as hydrocarbons, so they're both going to be molecules that contain hydrogen and carbon atoms only, but they're going to be bonded together in slightly different ways. Now, before we start anything, we need to know about 4 different prefixes in terms of naming. We look at the first one. The first one is meth. And if you have something starting with meth, that means that has 1 carbon atom in the molecule. The second one we're going to look at is eth. And eth means that particular molecule will have 2 carbon atoms in the molecule. The third one is prop, which is 3 carbon atoms in the molecule. And the fourth one is bute, and that is 4 carbon atoms in the molecule. Now that might not make sense at the moment, but as we go on, it will make a lot more sense. Now the most important thing is carbon is in group 4, so carbon is going to form 4 bonds. So for our first alkane, we draw our carbon and we draw the 4 bonds coming from our carbon. So that's really important. Whenever we're drawing alkanes or alkenes, every carbon atom must have 4 bonds, which are shown by these straight lines, each representing a covalent bond. So carbon must have 4 covalent bonds coming from it. So for our first molecule, carbon is going to be joined to 4 hydrogens. Now, because I have 1 carbon atom, the first part of the name of this molecule is going to be meth. And because it's an alkane, the second part of the name is going to be ane. So this molecule will be called methane. So it's an alkane containing 1 carbon atom. Now, if I look at the second alkane, first of all, if it's the second, I'm going to have 2 carbon atoms. So firstly, I draw my 2 carbon atoms bonded together with a single bond, because alkanes only have single bonds. Now, if I look at my first carbon atom, it has 1 bond there, so it needs 3 more bonds. So altogether, now I have my 1, 2, 3, 4. Then I do the same with my second carbon atom. I have 1 bond there already, so I have 2, 3, 4. So now that's good. Each carbon atom has 4 bonds, and those carbons are bonded to hydrogens. So I write my H for hydrogens at the end. Now for this one, because I have 2 carbon atoms, the first part of the name is going to be eth, because eth means 2 carbon atoms. And again, it's an alkane, so the second part of the name is ane. Now if I look at my third molecule, again, I draw my 3 carbons. Each carbon has to have 4 bonds. So I've got 1 there, 2, 3, 4. If I look at this carbon, it's got 1 bond there, 2, 3, and then 4. And then my last carbon atom also has to have 4 bonds. So it's got 1 bond there, then 2, then 3, then 4. And it's bonded to hydrogens. So where the carbons are not bonded to each other, they are then bonded to hydrogen atoms. And this time I have 3 carbon atoms. So the first part of the name is prop, and then the second part of the name is ane, because it's an alkane. And then lastly, for my fourth molecule, I have my carbon with its my molecule with its 4 carbon atoms. So I draw those first, and then again I need to make sure that each carbon atom has 4 bonds. So I've got 1 there, 2, 3, 4, 1 there, 2, then 3, 4, 1, 2, 3, 4, and for this carbon 1, 2, 3, 4. So all the bonds that are not the carbons bonding to each other are bonded to our hydrogens, because it's a hydrocarbon. So carbons and hydrogens only. And this one now, 4 carbon atoms. First part of the name would be bute, and the second part of the name is ane, because it's an alkane. So I have methane, ethane, propane, and butane, and those are my alkanes. Every carbon atom has all single bonds. If I consider my alkenes, my first molecule has to start with a carbon to carbon double bond. I cannot have that with 1 carbon atom, because you cannot have a double bond with 1 carbon atom. So we start with 2. Now the same rules apply. Each carbon can only have 4 bonds. So this carbon here has already got 2 bonds to the next carbon, because it's a double bond. So that means that this carbon can have 2 more bonds. So we've got 1, 2, 3, 4. You can draw these bonds upwards and downwards if you want, that's fine, but as long as this carbon only has 4 bonds. So I've got my 1, 2, 3, 4. And then I do the same with this second carbon. It's already got 2 bonds there, so it will have 2 more bonds. And because it's a hydrocarbon, the carbons would be bonded to hydrogen atoms only, nothing else in there apart from carbons and hydrogen atoms. Now if we look at the naming is exactly the same. I've got 2 carbon atoms, so 2 carbon atoms, the first part of the name will be eth, but this time we have an alkene, and ene means there's a double bond in there. So this now, instead of being ethane like as the alkanes with the single bonds. This is now called ethene. So this means we have a hydrocarbon molecule with 2 carbon atoms, and because it's an alkene, we have a double bond. Now, if I look at my next molecule, if we look at 3 carbons, so 1, 2, 3. Now, if I'm drawing my alkene with 3 carbon atoms, it doesn't matter if I put my double bond there or there. It makes no difference. So I'm going to choose to put my double bond here. Now, the same rules apply. Carbon atoms can only have 4 bonds. So if I look at this first carbon atom, I've got 1, 2, 3 and 4. If I look at my second carbon atom, I have 1, 2, 3 bonds already, so I can only have 1 more bond. So I'm going to put it at the top. You could put it at the bottom, but I've just chosen to put it at the top there. As long as there's 4 bonds, that's fine. And then if I look at my last carbon atom there, it only has 1 bond, so then it would have the second, third and fourth bond there. Now, we've got our carbon bond, so it's a hydrocarbon. It will only join to hydrogens now, because it's hydrogen and carbon atoms only. There we go. So I've got my 3 carbon atoms. Every carbon has 4 bonds. So this one now would be called prop, because it has 3 carbon atoms, and because it's an alkene, there's a double bond in there, it's propene. And for our last molecule, we have 4 carbon atoms. Again, we know if we're drawing an alkene, there has to be a double bond. Doesn't matter where you put it. So I'm going to put it in the middle, but you could have put it here or you could have put it here. So each carbon atom has 4 bonds. So we have 1, 2, 3, 4. So that's my first carbon atom done. My second one, 1, 2, 3, 4. For this next one, 1, 2, I'll put it at the bottom this time, 3, 4. And then for my last one, 1, 2, 3, 4. And because it's a hydrocarbon, those carbons are bonded to the hydrogens. So I draw in my hydrogens. And now for the naming, the start of the name, I have 4 carbons. So the start of the name is going to be bute. And because it's an alkene, it would be butene. Okay, so an alkene made up of 4 carbon atoms, an alkene made up of 3 carbon atoms, and an alkene made up of 2 carbon atoms. And then with my alkanes, butane means an alkane made up of 4 carbon atoms, an alkane made up of 3 carbon atoms, an alkane made up of 2 carbon atoms, and an alkane made up of 1 carbon atom. So we've got the displayed formulas where we've drawn it all out. We have our names. And now let's look at the molecular formulas. So for the molecular formulas, we just need to write how many of each atom we have. And we always write the carbon first, then followed by the hydrogens. So for the methane, if we look here, we have 1 carbon. Now if it's 1, we don't write a number. If it's more than 1, then we would write a number. So we have 1 carbon, so I don't need to write a number there. And if I look at my hydrogens, I've got 1, 2, 3, 4. So that would be CH4. So you make sure the 4 is small, just after the atom, and that tells me I have 4 hydrogens. If we look at ethane, for my carbons, I have 2, so I put a 2 there. And then for my hydrogens, for each carbon, I've got 1 below, 1 above, so twice as many, plus the 2 on the end. So if I've got twice as many plus the 2 on the end, 2 times 2 is 4 plus 2 would mean I've got 6. For my propane, I have 3 carbon atoms, so C3. And for every carbon atom, I have a hydrogen above, hydrogen below, so that's twice as many. So that's going to be 6 plus my 2 on the end. So that would be C3 and then H8. And then for my butane, exactly the same. I've got 4 carbon atoms, and for every carbon, there's one below, one above, and then my 2 on the end. So if I've got 4, double that up, that's going to be 8 plus 2, that's going to be 10. So these are the molecular formulas. Now, if I do the same for my alkenes, if we look at our first one, I have C2, and then I have H4. For my propene, I have C3 because it's propene, so I know I've got 3 carbon atoms. If I count my hydrogens, I've got 1, 2, 3, 4, 5, 6, H6. And if I look at my butene, because it's but, I'm going to have 4 carbon atoms, and if I count my hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, H8. So for the alkenes, it's just twice the number of hydrogens as you have carbons. Now, if I write these as a general formula for my alkanes, okay, we're going to use C and an N. N could be any number. So it could be 2, it could be 4, it could be 6. So we're just going to use N for meaning any number. Now, however many C's we had, we said you're going to have twice as many H's. So if I had 5 carbons, twice as many would be 10. If I had 10, twice as many would be 20. So however many carbons you have, you're going to have twice as many. So 2N, twice as many hydrogens, plus the 2 extra at each end. So the general formula for an alkane is CnH2n plus 2. So for example, if I said I had an alkane with 15 carbon atoms, what is the formula? It would be C15, because that's how many carbons I have. Then to work out my hydrogens, it would be 2n, so 15 times 2 would be 30, plus 2 would be 32. So the formula would be C15H32. Now, if we look at the alkenes, this one's a little bit more simple. So however many carbons we have, for our hydrogens, we just have twice as many. So if I had 15 carbons here, I would have 30 hydrogens there. So however many carbons you have, it's twice as many hydrogens. So I've got 3 carbons there, 6 hydrogens there. I've got 4 carbons there, 8 hydrogens there. And for my alkanes, I've got 4 carbons here, and here I've got twice as many plus 2. So 2 times 4 is 8, plus 2 is 10. Here, 2 times 3 is 6, plus 2 is 8. And here, 2 times 2 is 4, plus 2 is 6. And here, because I've got 1 carbon, 1 times 2 is 2, plus 2 is 4. And that's everything that you needed to know about alkanes and alkenes in terms of drawing them out, their formulas, and these, which are called their general formulas. In terms of the properties of alkanes and alkenes, there's one key thing that alkenes will do that alkanes will not, which helps us to identify an alkene from an alkane. Now, the reason why we might want to do that is in terms of alkanes and alkenes, we may have two solutions where we don't know which one is an alkane and which one is an alkene, or we may just want to know if it's an alkane or an alkene. So if I've got this one, which is an alkane, I would have a clear liquid in there, and if I've got this one, which is an alkene, it would also be a clear liquid. So there really wouldn't be a good way just by looking at these to distinguish which one's which. So what we can do is there's a very specific test to differentiate the alkenes from the alkanes. And what we do is to each of these substances, we would add some bromine water. Now, bromine water is like a browny orangey colour liquid. So you add a few drops to each one. If it's an alkane, all that would happen is the bromine water would become diluted in the alkane. So you put it in, give it a bit of a shake, and you wait to see what happens. And all that happens with an alkane is the bromine water, which is an orange browny liquid, just dilutes. So it will just look a paler orangey browny coloured solution in there. However, when you add your drops to the alkene and you give it a shake, with the alkene discolorizes. So the alkene would be colourless. So when you put it in, you might see a pale brown orangey colour, but as you shake it up, it discolorizes. That means it becomes a clear liquid with no colour. And that is the test for an alkene. Alkenes discolorize bromine water, whereas alkanes will not do that. So now let's consider the process of cracking. Now, cracking is simply just what the name suggests. We are breaking down long-chained hydrocarbon molecules into smaller chained molecules. So for example, if I've got this long chain hydrocarbon molecule and I crack it, I am simply going to break it into smaller hydrocarbon molecules. So now let's consider the actual process of cracking. So we start off with our long chained hydrocarbon. So we've got C8H18. So it's 8 times 2, which is 16, plus 2, which is 18. We have our alkane to start with. This is then going to break into 2 smaller chained hydrocarbon molecules. Now, if we look at the products of cracking, first of all, for our alkane, we started off with 8 carbon atoms. And if we look at our products, we have 5 there and 3 there. So altogether, I still have my 8 carbon atoms that I started with. I started off with 18 hydrogen atoms. So if I look here, I've got 12 hydrogens there and 6 hydrogens there. So that gives me my 18 hydrogen atoms at the end. So it's important to remember that the number of atoms that we have at the beginning is equal to the total number of atoms that we have at the end. And when we crack long-chained hydrocarbon molecules, we always produce an alkane and an alkene. So you always get an alkane and an alkene. And the alkenes can then be used to join together to form polymers. So lastly, we're going to look at the complete combustion of our hydrocarbons. So what this means is that our hydrocarbon would be reacted with oxygen, and when that happens we would have carbon dioxide being produced as well as water. When the hydrogen becomes oxidized and becomes water, H2O, the carbon becomes oxidized and becomes carbon dioxide. You may be asked to balance an equation to do with the complete combustion of a hydrocarbon. So for example, if we had CH4 plus O2 produces carbon dioxide, which is CO2, plus water, which is H2O. Now, the key thing is whatever we have on the left-hand side has to be the same as what we have on the right-hand side. So the atoms that we have are, we have carbons, we have hydrogens, and we have waters. So if we look on the left-hand side, we have one carbon atom, and if we look on our right-hand side, we have one carbon atom. So at the moment they look balanced. However, now if we look at our hydrogens, on the left hand side we have 4, however on the right hand side we only have 2. Therefore, to balance out our hydrogen atoms here, we would need to have 2 H2O molecules. And that now, 2 times 2 means we have 4 hydrogens on the right hand side and 4 hydrogens on our left hand side. We've still got 1 carbon and 1 carbon, so everything's balanced so far. Now if we look on our left hand side, at the moment we have 2 oxygens, and on the right hand side we have 2 oxygens there plus our 2 oxygens here, so we have 4 oxygens altogether. So that means for our oxygens to balance out we would need 2 O2 molecules, because 2 times 2 now is 4. So that is our balanced equation. So now let's have a go at some questions. If we look at this first question, it says describe how crude oil is separated using fractional distillation. So the first key point to mention is we heat the crude oil to make sure it is vaporized. Then the gases with the lowest boiling points rise to the top, where they condense and are collected. The fractions with the highest boiling points will condense and be collected lower down the fractionating column. So the trend is the lowest boiling points go to the top and the highest boiling point fractions are lower down in the fractionating column. Now if we look at our next, now for the next question, we are being asked to draw a ring around the part of the molecule which makes the propene unsaturated. So it's unsaturated because it has a double bond, so that is this part here. Then the bromine water changes colour when mixed with an unsaturated compound like propene. We've got to complete the sentences using the words. So before mixing with propene, bromine water is, and that would be an orange colour. So if we write our orange colour in here, oh, the O's gone missing, let's put that back in. Okay, and then after mixing with propene, the bromine water would go colourless. So we just write that in there. Now in this question we are looking at some crude oil, which is a mixture of hydrocarbons. Hydrocarbons can be used as fuels. Now one alkane has 34 hydrogen atoms, and we've got to work out which one of these formulas would be the alkane. So if we remember, for alkanes, however many carbons you have twice as many hydrogens plus 2. So if we take away 2 from 34, that leaves us with 32, and then if we divide that by 2, that should tell us how many carbons we have, which is 16. So our answer would be this one here. So in this next question, we are being asked to describe which type of reaction is being shown here. Now here we can see a large hydrocarbon molecule is being broken down into smaller hydrocarbon molecules, so this would be cracking. Now in this last question, we're being told that methane is burned in a plentiful supply of oxygen, so that means we have complete combustion, and we've got to say which is the correct balanced equation. Now first of all, if we look here, we have CH4, so we need to make sure we have 4 hydrogens on the product side. So this one only has 2, so it cannot be this equation. This one only has 2, so it cannot be this equation either. Now if we look at the last two, our carbon in this first one here is now balanced out with the right hand side. So we have 1 carbon on the left hand side, 1 carbon on the right hand side. We have 4 hydrogens on the left hand side and 4 hydrogens on the right hand side. We have 4 oxygens on the left hand side, and we have 4 oxygens on the right hand side, because we have 2 in the carbon dioxide and we also have 2 water molecules. So that gives us 4 oxygens altogether. So our balanced equation would be this one.